All right, guys, so this afternoon, okay, you guys are going to look at what we call current. And I'd imagine you guys have seen current before. Uh, Conceptually, not too bad. It'd be like the flow of cars on the road almost, right? And we're going to like work that into our analogy that we started this morning later. Um, but for the purposes of electricity, we can see that current can be defined as the amount of electricity or the number of electrons flowing through a wire in some amount of time. Okay. And to calculate how much current is happening, right, or going through a particular point in a circuit, we can look at this equation where I, the amount of current, right, is equal to Q divided by delta T, right? Which basically says that we want to look at how much charge, right, the number of coulombs are passing through a particular point in time for that time, or a particular point in a wire for a particular time, unit of time. Okay, so we can see that the units, the charge per unit time, seconds, okay, which means charge per unit time, okay. Now, typically, as we move forward in this unit, we will see that the direction of flow for a circuit goes from the positive lead of a battery to back to the negative. Okay. The way I kind of think about that is like we've gained electrons in the battery, or gained potential energy in the battery. So we leave with positive, and then we lose it all over the course of the circuit, right? And we come back with a loss. That's kind of how I remember that. So yeah, you can see kind of the flow of the electrons in the wire there in a picture. Okay. Now I just want to revisit something, right? If we were to set up a simple circuit with a battery and a light bulb, we could attach an ammeter. An ammeter is like, looks like the voltmeter that we saw this morning, right? And sometimes they are the same machine. You can change what it is you're actually measuring. If you're measuring voltage, resistance, or current, right? You can, there's the little dial there lets you pick what it is you're actually reading off. But the one thing we kind of want to recall from lesson 1 is what a coulomb actually looked like, right? A coulomb was a combination of many electrons, right, condensed into kind of a unit of a volume, right? And so if I were to get a reading, like if we were to like the units for current are or the ammeter or amps, right? 1 amp would be equal to 1 coulomb per unit time in seconds. Okay, so if I was to set up a circuit, a simple circuit, and I had electrons flowing through that circuit, right, and the light bulb was lighting up, if I put my ammeter across the circuit, I would see in this particular question a 0.25 reading, right, which basically means 0.25 amps, which means I'm receiving 1/4 of what that was per unit, or per unit time, in this case seconds, right? Seconds. So we're seeing this number of electrons flowing through that particular part of the wire every second. Okay, so after 4 seconds, I would have seen 1 entire coulomb go through that wire. Okay. So what I liked about this picture is that well, 2 things. One, we revisit what a coulomb actually looked like, right? And just how many electrons made up 1 coulomb, right? And we saw from the voltage lesson this morning how we came up with the charge of an electron, right? But then if we take a look at that, this is a nice depiction of like what would 0.25 amps look like. Well, it's 1/4 of that coulomb, right? So that's that. If I come down here, we'll see that like there's just some as reference things here, right? Like, so how much current and what you could expect to see given different amounts of current going through your body, right? So everything from 0.0008, which is a slight tingling, right, all the way up to like half an amp, right? Remember, half an amp as reference would be half of this thing, right? So half an amp would cause possible heart fibrillation, right? So like you'd have I don't know, I'm not a doctor, right? You'd have problems with your heart, right? Just from that. Like, that's a lot of electricity. If you think about that, that's like even half an amp. These are people contextualizing what half an amp is. Like, that doesn't sound like a lot, but like, look at half. You're getting half of this box every second, right? And we saw what the charge was on each of those little electrons, and like how many of those electrons are in one coulomb. You know, you cut that in half. That's a lot of electrons going through you every second, right? Significant, right? And so that causes problems. Okay, so what we want to do here, right? What's the end goal here? So some of these lessons are a little bit smaller from the standpoint of like, and I'm going to give you some supplementary videos to watch. But the end goal here is to be able to say, here's a circuit. Can we take things like, how do I calculate the amount of current in a wire and apply it to that that simple circuit, right? So everything like, well, what's the current? What's the voltage? What's, you know, bouncing around and solving for different values across a simple circuit is the end goal here, right? What we're doing here is to try and build you up to that, okay, so that we can get some experience working with some of these equations. Okay, so we've seen now that a coulomb, an amp meter, so one amp is equal to like the coulomb, 1 coulomb of charge or whatever it is per unit time, right? That's what we care about. It's the charge per unit time. We saw that up here, right? And so what we want to do is we're going to use that, right, to our advantage, right? There's no memorizing. We know conceptually, if we think about this from the standpoint of like an amp is the amount of current flowing through a wire, then we need to think about, okay, well, there's a charge flowing through that wire per unit time, and that tells us how much is going through the wire every second, okay? And so we don't have any memorization in terms of the equation, right? We know that the equation must follow suit in what we've written here, right? Well, I has to equal the charge we denoted as Q over T, or delta T, right? We can even change this to seconds, coulomb per second. Okay, and so what we're going to do here is we're going to just apply this equation, right? Now the thing is, why I wrote this here is because we see what our units have to be in order for an amp to be usable, like to actually get an answer of an amp, right? So we can't use things like millicoulombs and we can use things like minutes. Like 1 amp has to be coulombs per second, right? And so those units that we've got there aren't useful to us at their current state. So we got to convert them, right? We got to get coulombs per second. Okay, so we got to convert the millicoulombs to coulombs, and I got to convert this 0.75 minutes to seconds. Well, let's start with that one because that one seems okay. You'll recall 0.75 would be 3/4 of a minute, which you guys know as being 45 seconds. Okay, and then the millicoulomb, if I just write this out, I taught you guys a little bit of a trick. Like, this is a millicoulombs. Milli means move the decimal 3 to the left, which you guys have probably done before. So let's take our decimal and go 1, 2, 3. Fill in the bumps with zeros. There's your answer in coulombs. Okay, so now if I go to find the amount of current flowing through this wire every second, I have my dimensions will check out, if you will, right? Like I have my coulombs and I have my seconds, so all I have to do is find I. I will equal the charge 0.0002 coulombs divided by 45 seconds. And we find that the amount of current going through the cell phone charger would be 4.4 times 10 to the negative 6. Okay, and so if I were to write, that'll be amps, right? And if I was to write this, I just want to make a little comparison to you. Because all this information is stated on the back of chargers and things, right? Like you get like what the voltage is, you get like current and things like that, right? You could work through what would happen if you were to actually touch this, and so we know. I'm just going to convert this. Sorry, I'm just thinking. I want to turn this from scientific notation into just a decimal number so that I can compare it against our chart up above, right? So that is 4.4 times 10 to the negative 6. I'm going to move the decimal place to the left 4. So 0. Oh, nope. So that means I'm going to have 5 zeros, right? 1, 2, 3, 4, 5, 4, 4. Right? So you can check that by going 1, 2, 3, 4, 5, 6. Okay, we're good. Okay, so that's what that would look like in standard form. This is just a number. So let's just have a look here. You know, you're getting a slight tingling at 3 zeros. Well, we're like way below that. Okay, so are you going to feel anything off the cell phone charger? Probably not. Okay. And just a summary here. Okay, so direct current is the flow of electrons. We didn't necessarily actually discuss this. I think I put it somewhere on the side though, and I just missed it. Oh, I didn't. Oh, yeah, I did. Okay, so the direct current is the flow or movement of electrons in one direction. Okay, and we'll come to learn about alternating current, where the electrons can flow this way, but then they can also flow this way as well. That's alternating current. Okay, but for our purposes, we're just going to have a look at direct current for today. Okay, so it's the flow of electrons in one direction only. That goes from the positive lead back to the negative, right? The symbol for current is I, and current is measured in the units of amperes, okay, or amps. And the equation that describes that is I is equal to Q over T, and we can see when we start labeling circuits, this is here just for your benefit. So when we draw in amp meters or voltmeters or whatever it is we're drawing in on our circuits to measure whatever it is we're measuring, that's how you would label an amp meter. Okay, they're measuring the amount of current passing a particular point on your circuit. Okay. So the last part of this, and this is kind of the fun part that keeps all this stuff straight in my head, right? Because if I were to try and like remember this all the time, I mean, conceptually now it's not too bad. Now that I have a little bit better math understanding, right, and dimensions and what I'm trying to convey to you guys. But this was like I was scared of this unit until I saw this analogy. Okay. And I'm just going to allude to something I said at the beginning of this little lesson, okay, not too big. That current you can think of as being like vehicles on a road. Okay, and we saw the first piece of our analogy this morning. We're going to like continue to build that analogy until it's like very, very clear when we jump to the circuits, what information is doing what. Okay, you're never going to mix anything up. So, current is cars or trucks, right? They're going to be the carriers of joules, right? So energy. They're carrying energy from the bank around a delivery route. The delivery route is the circuit that we're going to set up, right? And so the cars leave the bank or the battery where they've picked up joules of energy, right? And then they're going to drive around the circuit or the track or whatever the delivery route, right? And they're going to return back to the bank or battery, right? And the process is going to start over again, okay? Where we're going to start to see things increase in terms of how interesting they are is when, we introduce things like light bulbs or resistors, and that's going to be a different lesson. That's tomorrow's lesson, okay? So I'm a firm believer in this analogy. It's kept it straight in my head since day one, and I kind of find it joules and joules I find funny, and bank and battery I find interesting as well. Okay, and volts I find that funny. Okay, it keeps it all straight in my head, right? So you guys will you'll come to appreciate this analogy when things get a little bit more complicated, and we're able just to talk about things in terms of the analogy. It'll make sense. Okay, and direct current means it's a one-directional delivery route. Okay, so the cars can't just flip around and start driving in the opposite direction again. Okay, so that's a crash course on current, how to use it, what it's measuring, how to measure it, and how to do some calculations on it. Okay, and I'll put a little bit more of a supplementary video too as well, and the analogy at the end there is going to come into play over the next few days. Okay, so that's that. You guys let me know if you have any questions. Below here you have some questions to work on as well. 1, 2, 3, 4, and 8. Okay, and that'll be your homework for this lesson. Okay, and that's that. You guys let me know if you have any questions.